Another analysis that we can do to determine whether there are any variables that we can throw out is correlation analysis. So when two variables are highly correlated, they have overlapping information. So they are redundant. These two predictors are redundant. One of them we can keep, the other one we can throw them out. So that's the reason why we do correlation analysis. And such a situation is referred to as multicollinearity. So the presence of multicollinearity becomes two or more variables are sharing the same linear relationship with the outcome variable, the target variable. So removing the variables that are strongly correlated with each other will improve the accuracy and reliability of the model. So if two variables are highly correlated, and which one should we keep? Okay, again, you can use information from domain area expert and also see which of the two variables has a higher correlation with the target. The one that has a higher correlation with the target, now you keep. The one with lower correlation, we can throw it out. So here is an example of a correlation matrix that we looked at from the previous chapter, and where we have the correlation matrix and use conditional formatting to highlight the variables that are highly correlated. Highly correlated here means either on the positive side or on the negative side. The high negative correlation is also bad, and like high positive correlation. Okay, another approach that we can use to reducing the dimension is reducing the categories. Suppose if you have, we talked about this, suppose if you have a categorical variable with 10 categories, right? So 10 categories means you need 9 dummy variables. If that column, instead of having 10 categories, if we can combine some of those categories such that we end up with only 5 categories, then that will result in only 4 dummy variables. So we have reduced 5 variables. You have reduced the dimensionality by 5 variables. So that's what reduces the number of categories mean. A single categorical variable with m categories is transformed into m minus 1 dummy variables. Then we end up with too many dummy variables, so reduce by combining the categories. Okay. The exception is naive Bayes, which does not need dummy variables. It can handle categorical variables as is, unlike regression and so on, where you need to convert the dummy variables into categorical variables into dummy variables. So here is a way of figuring out which categories can be combined. So we look at an Excel example. We'll go through this in another exercise, where we have zoning data ZN converted into distribution chart, where each value is plotted from 0 to 100%, and the distribution is cat med v. So which means for each Zn value, what percentage of Zns are cat med v 0 and what percentage is cat med v 1, right? So if we have similar pattern, okay, like for example here these three are identical, so we can combine these three, okay, and these two. So okay, look at these two, 34 and 35, they are identical shape, so these two can be combined. So by looking at a distribution chart like this, where each value of the categorical variable is plotted with respect to the target, so what proportion of that particular value is category 0 and what proportion is category 1, and we can examine the similarities in these bars, and using that information we can combine categories.